This video is about modeling with linear systems and two variables. Modeling is a fancy word for word problems. So we're going to start our notes with some guidelines for modeling. And these guidelines are true generally speaking. We'll see some examples that follow to help us see them come alive here. But the steps are as follows. First, we're going to identify the variables, or you could say define variables. This will be related directly to the question being asked, as we'll see. Secondly, we're going to create equations or express all unknown quantities in terms of the variables. Thirdly, we're going to set up a system of equations which flows naturally from having the equations in step 2. We'll see some nice tricks as ways to do this. And then fourthly, we're going to solve the system and then interpret the results to make sure everything's making sense. Let's consider an example which reads as follows. A boat on a river travels downstream between 2 points, 20 miles apart, in 1 hour. The return trip against the current takes 2.5 hours. What is the boat's speed, and how fast does the current in the river flow? So there are two questions here, and we want to target those two questions to help us get started, right? They want to know what is the boat's speed. Well, if that's a question, then we want to define a variable that would answer it. So let's let b equal the speed of the boat. Really, you could use any variable, x, y, whatever, but b for boat seems to make sense. So b is the speed of the boat, but the second question was, how fast does the current in the river flow? So why not c for current? So we'll say c is the speed of the current. And this is what is generally known as a distance, rate, time problem for obvious reasons. If you read the problem, it involves distance, rate, and time. Rate's another word for speed. And generally speaking, there's a known formula for this, which is distance equals rate times time. If you multiply rate times time, you get distance. That's just the definition in our known universe that we use, okay? So there's another convenient way to organize these kinds of problems that's often used, and that is to use a chart. So I want to demonstrate this chart method where we'll use 2 rows in this chart and 3 columns. Now, see if you can figure out why there might be 2 rows in this chart. I'll give you a hint. There aren't 2 boats. But think about the problem a little bit about that. So it's not like we have boat 1 and boat 2. What's going on in this problem? Across the top, okay, I'll let you think about that for a second. Across the top, we're going to use our formula. And though you could put this in a couple different ways, I like to go rate times time equals distance. Just a nice, using the formula here, it's a nice way to set it up. Okay, have you thought about the reason we have 2 rows? We don't have 2 boats, but we have 2 trips, right? A boat on a river travels downstream, but then there's a return trip going upstream, which is also known as against the current. So why don't we label our 2 trips as up and downstream? I'll just put up and down arrows to represent that, but that's really what's happening. So now, let's also consider what's going on. You have a boat traveling either with the current, that's downstream, or against the current, that's upstream. So that will affect the overall rate of this boat. If you've ever been on a river in a canoe or something, you know this. The current does affect the boat speed. Or the same thing happens if you just walk with or against the wind. It's the same kind of thing. So, all right, if you're going upstream, that's against the current. I've chosen the top row of our chart to represent the upstream. It doesn't really matter which row you pick for up and down. The rate upstream is going to have to be slower, which we're going to represent as the boat speed b minus the current, right? The current is working against the boat, so we subtract the speed of the current, that's c, for the overall rate. So our rate going up is b minus c. Now, the time going up, if we can kind of continue along this top row, they do give us some indication here. The boat travels downstream in 1 hour. The return trip against the current, that's upstream, takes 2.5 hours. So we'll put 2.5 as our time going upstream. Notice they say that there's 20 miles apart between these 2 points. So that means our distance going in one direction would be 20 miles. So we'll put in 20 for the distance spot. All right, that fills in our top row, which is the upstream information. Now downstream, you might imagine it's very related, but the current is now pushing the boat. That's what it means to go downstream. So that overall rate is going to be faster. It's going to be the boat speed in still water plus the current speed, so B plus C. And naturally, we would expect this to go a little faster. And they say that the downstream time is 1 hour, so that's just 1 for the time going down. Now, the distance should be the same if this is a return trip, so we'll say 20 there as well. Okay, now filling in the chart is important, but it's really not the whole problem here, or even the solution. The rest of this is going to be creating equations and then using those equations to solve. But the good news is that each row in our chart represents an equation, and we'll find it by using the formula that's above our chart. So if rate times time equals distance, then let's take this top row in our chart and multiply the rate cell times the time cell to equal the distance cell. In other words, I could say 2.5, that's the time. I'm just rearranging this so it looks better, but I'm multiplying really the rate and the time cells together. So 2.5 times B minus C. It just looks better to put the number in front of that, parentheses. That's the product of rate times time equals the distance, which is 20. Okay, but then the second row will create a similar equation where this time I have 1 times B plus C equals 20. That's again multiplying the rate times the time in the second row. And then this result really gives me a system of 2 equations, but they don't really look familiar in terms of stuff we've been doing with systems yet. We should really distribute the numbers in these parentheses just to make it look a little more familiar. So let's do that. In the top equation, we'd have 2.5b minus 2.5c equals 20. And in the bottom equation, we'll really just have b plus c equals 20. If you distribute 1, it doesn't really do anything. So this is now the system we want to solve, and we could use really any of our methods, being substitution, elimination, or addition, even graphing, but these are, when you get decimals involved, it's harder to do an accurate graph. So given the way these are set up, especially kind of looking at this second equation, it would be pretty easy to solve it for either of those variables. I would say that's a pretty good hint that maybe substitution is going to be the cleanest method here. So we'll say here, let's try substitution just to see if that method will do as well as we think it might. Again, the reason we're picking it is because the second equation almost has a variable alone, and that's the first step in substitution. So if I solve for b in that second equation, that means I would have b equals, I could subtract c from both sides. I'd have b equals 20 minus c. If that's the case, I'll substitute that expression for b into the other equation, which would then read 2.5 times b, but b now is really 20 minus c, minus 2.5c, just keeping with that, how that equation is, equals 20. But notice now there's only a variable c, which we should be able to solve for. So we'll distribute and see if we can solve for here. 2.5 times 20 should be 50. So 50 minus 2.5c minus 2.5c again. Okay, don't get lost here. This first minus 2.5c was from the distribution in that first binomial parentheses in that prior step. The second minus 2.5c is coming directly from what was in that equation. Okay, so let's not get that confused. We have 2 minus 2.5c's on the left side of this equation. That all equals 20, the number we had over there originally. So now we'll continue. This really means that 50 minus 5c, if we combine those like terms, negative 2.5c and negative 2.5c, this all equals 20. So now we'll subtract 50 from both sides and get negative 5c equals negative 30. If we divide by negative 5 on both sides, then we'll end up with c equals 6. Now remember, our whole point was to find two things, the speed of the boat, that's B, and the speed of the current, that's C. So we found C. We should be a little more descriptive though. If you go back and check on the units, it looks like the distance given is in miles and the time is in hours. So we can say comfortably 6 miles per hour is the current, the speed of the current. So at least now we're describing our answer. That's part of what we were being asked. Now the boat speed we could find by going back to our equation for B, which we already had solved for above. So now we'll say B equals, and it was 20 minus C. So now we can say comfortably that means 20 minus 6, which means B equals 14. Again, miles per hour would be our units, and this would be our boat speed. So we found the current speed, we found the boat speed, which means we are good to go. And we did it using this process for solving word problems, where we define the variables, create a system of equations with some help from that chart, and then simply solve the system. Let's try another example. This time it reads as follows. A man invests his savings in two accounts, one paying 6% and the other paying 10% simple interest per year. He puts twice as much in the lower yielding account because it is less risky. His annual interest is $3,520. How much did he invest at each rate? Okay, well, this is not a distance rate time problem, as you can probably guess. This is a different type. This is a type, you could call it interest, you could call it investment. It's all about the same type here, but the interest type of problem has a formula, and that is the dollars invested times the percentage rate for the interest, but as a decimal, equals the interest amount, which you could also call the income. The interest income, that is. Okay, so there's our formula. And we're going to organize this one with a chart, just like we did with the distance rate time. This is just a convenient way to organize things. Now, the reason we have two rows this time is because we have two different accounts. It says one's paying 6%, so we're going to label these outside of our chart on the left side as 6%, and one paying 10%. And then we want to put our formula across the top. So we're going to put our dollars invested, also known as principal. We're going to put our percentage interest, but remember, we're going to use that as a decimal, and we're going to multiply those together, and that product is going to equal our income, or the interest income, you could say. So there's our formula, there's our chart. Now let's go back and see what we can plug in from the given information. It says a man invests in two accounts. Okay, got it. 6 and 10%, got it. He puts twice as much in the lower yielding account because it's less risky. Okay, that would be the 6% then. Notice we don't know how much he put in either account, but we know he puts twice as much in the 6%. So a convenient way to do that, or represent that, would be to say, how about X in the 10% and 2X in the 6%, right? Wouldn't that mean twice as much in the 6%? Where we let X equal the amount he invested in the 10%. Okay, so that takes care of that sentence. But then it also says his annual interest is $35.20. We're going to have to include that as well. Now the percentage column will be, remember, that's the percents written as decimals. We already have that information. So 6% would be 0.06 as a decimal, and 10% would be 0.1 as a decimal. The income, notice, we have a combined total, like his annual interest income is $35.20, but we don't put that in each account because it sounds like that's what he got total for his annual combined interest from both accounts. So instead of putting $35.20 in both income places, we're going to represent the income from each account using this formula. So we'll say dollars times rate equals income. In other words, for the first row, that's going to be 2x times 0.06. That's just multiplying each of those cells together. That's an x, not a times there. 2x times 0.06. In the second row, it's just 0.1 times x, or in other words, 0.1x. And then what we can say is that the income amounts, which are represented in the two columns cells for the income column, together should come out to be the 3520 amount that he got for his annual income. So we can put this all together and say 2 times x times 0.06, that's the interest income amount for the 6% rate, plus the expression for the other account was the 0.1x. If you put those two accounts together, the total income as given was 3520. Now we want to just simplify and solve for x. So 2 times 0.06 would be 0.12x plus 0.1x equals 3520. We'll combine like terms and get 0.22x equals 3520. Now we know we're going to want to divide both sides by 0.22 to solve for x. So we'll go ahead and just do that on a graphing calculator and type in 3520. That's the right side. We're going to divide that by 0.22, and it turns out to be 16,000. So if x is 16,000 as given by the calculator, that tells us something. That tells us, remember, x was the amount that was invested in the 10%. Now the question was, how much did he invest at each rate? Well, there's half our answer. So we can say $16,000 was invested at the 10% rate. Then obviously the rest would be the other one. So if x was 16,000, the other amount was 2 times x, which means we could say 32,000 at the 6% rate, and that would cover both of the accounts given in this problem.